Hi, welcome back everybody. It's time to introduce some calculus into our problems in calculating electric fields. So, in other words, we're going to be dealing with continuous charge distributions rather than just adding up a few Coulomb's law type electric field expressions. So, we'll begin with a few easy situations. In fact, we're just going to look at the somewhat easy situations in this video, and then we'll look at some of the more difficult ones in future videos. So let's say we have a bar of charge, and we're going to first off pretend that the charge is uniformly distributed along the bar in this example. The next example we'll look at what we would do if it's not uniformly distributed. So in general with these types of problems, the idea is like, well, wait a second, I know how to calculate the electric field due to a point charge. So if it was a point charge, each point charge would just contribute a kq over r squared magnitude times a unit vector going from the point charge to the direction that in space that we're interested. And the r would be the distance between our point charge and that point in space. So it's like, okay, if I have a continuous charge distribution, what I'm going to do is I'm going to divide it into a whole bunch of little bitty charges. And I'm going to call each of those dq. The magnitude of each of those charges is dq. Well, what would be the electric field due to dq? Well, that would just be k times dq over r squared, where r is the distance between dq and my field point, or my point in space where I want to know the field. And then we would have to figure out exactly what dq is, because I mean you're going to find that you're not going to have a dq or a q axis or anything like that. So we're going to need to express it in terms of something else most of the time. And after we do that, we will then calculate the net field by summing up all of the fields due to each of those individual little bitty dq charges. How many dq charges will there be? Well, they're actually going to be infinitely many, which is why, in general, our sum is really going to turn into an integral. So now, back to this example. We have a bar of charge that's where the rightmost point on the bar is at the origin, the leftmost point of the bar is at x equals negative q. So here's our situation. Now I'm going to rename our axes. I'm going to call the horizontal axis x prime and the vertical axis y prime, because what we're interested is finding out what is the electric field at any point x on the positive x-axis. Well, if I'm going to consider it at some particular point x, then it's a good idea to rename my axes. So I just decided to call the axis the x prime axis. So what that means is, let's say I want to know my distance between this little bitty amount of charge that's right underneath this arrow. What's the distance between dq right here and x? Well, the position of dq right here is at a position of x prime. So whatever my x prime is right there. So the distance, therefore, is going to be x minus x prime over to here. So I'm over x over here. I'm to my particular point x. I'm over x prime over here. So x minus x prime. That's my distance, my r value. So how much dq is there? Well, those of you who already know a good bit of integral calculus recognize that, okay, we're going to need to integrate along the x direction, or the x prime direction, if you will. But, I mean, I just wrote down a charge dq. How does dq relate to x prime? So here's the idea. We're going to assume that our bar of charge is infinitely thin. In other words, it's not thick enough that we need to take into account any off-axis charges. So all the charges along the x prime axis. So the amount of little bitty charge there, it's going to be given by in terms of a linear charge density, which is usually signified by lambda, the lowercase Greek letter lambda. So the amount of charge that's there is equal to whatever the charge density is times the size of that charge density, or that little bit of charge, I should say. It's kind of like how back in physical science, you got used to the fact that density was defined by mass divided by volume. Well, you could solve for the mass and say, okay, mass is equal to density times volume. Well, here it's not mass density that we're dealing with, it's charge density. So it's not how much mass, it's how much charge is there. So the amount of charge that's there is equal to the linear charge density times the size of that particular charge. Well, if the charge is a little bitty amount of charge, dq, it's going to take up a little bitty amount of space, dx, or in this case, dx prime. So the amount of charge that's there for dq is equal to the charge density, lambda, at that location, times dx prime. In fact, that really just kind of goes into the definition of what lambda itself is. Lambda is defined to be dq dx. So, since in this example this is a uniform bar of charge, you can say, oh, I know what lambda is for a uniform bar of charge. It's just equal to the amount of charge on the bar divided by the length of the bar, Q over L. So yay, I know what lambda is for this particular example. So I can plug that in for my lambda and say that, okay, wherever I have a dq, I can replace that by Q over L times dx prime. Now, keep in mind, yeah, as I mentioned before, it's a good idea to rename our coordinate systems. A lot of times textbooks ignore this, but it's something that I think is important, because you don't want to name a particular point on your axis the same as the name of the axis. So that's why we like to rename these things. But the reason I mention this again is because when we put a prime on a coordinate here, that's not denoting taking a first derivative or anything like that. It is simply a renamed dummy variable coordinate. So, what about this linear charge density? So as I mentioned before, the definition of linear charge density is just dq dx, or dq ds in some arbitrary coordinate space. So because of that definition, we have that dq is lambda dx, and in this case our coordinate is x prime. Now, the reason I mention this is because a lot of times you'll need to keep this in mind if you don't have a if you don't have a constant charge distribution. So, in other words, pretty soon we're going to encounter a situation where lambda itself is a variable. So we're going to be plugging in dq is equal to lambda dx, but lambda, being a variable, is going to have some sort of functional form. It's not just going to be a constant, which means you won't be able to pull it out of your integral necessarily. In this problem, though, you will be able to. In fact, that's just a q over L, which we're going to just plop right out of the integral. Okay, so back to the problem. Well, we know the electric field due to a point charge. It's kq over r squared. So the little bitty electric field due to a little bitty point charge dq is going to be k dq over r squared, or r again is x minus x prime. And dq was lambda dx, or well, better yet, lambda dx prime. That should be called an x prime right there. So q over L dx prime. So then we're going to add all of these things up using an integral. Now, students who are caught using their cell phone during class will not be allowed to use an integral. Instead, they're going to need to write out each of those infinitely many terms and add them up by hand. Okay, so on with this. The bar has a length of L, and it goes from x prime equals negative L to x prime equals 0. So the total electric field contribution due to all the little bitty charges on the bar is equal to the sum of each of the little bitty contributions from each of the little bitty charges, each little bitty contribution being dE. So a fancy stretched out sum is the integral sign, and when you see that, that means that we're dealing with a continuous distribution. So I'm going to plug in my expression for dE. So I just take this, I plug it in right here. I factor out the terms, or I'll pull out the terms that are constant. In other words, K, which Coulomb constant is as constant as they come, times Q over L. So those are constant in this problem, and we pull them out. Now we're left with this term right here, this x minus x, this integral right there. So this is a situation where we can solve this by U substitution. Now, if you're not familiar with what U substitution is, never fear, because you will have an integral table present. In other words, once you see a function that's in this form in an integral, you can just look it up in the table. We're going to talk about using integral tables soon. So in any case, we're going to do a U substitution to turn this into something that we're more familiar with, where we substitute U equals x minus x prime. Now notice that my coordinate is x prime, so we need to keep that in mind. We need to express our u's and our du's in terms of that actual coordinate. So, well, if I'm doing this variable substitution, then, well, that's not a du. I need to turn it into a du. Well, what would du be? Du is negative dx prime. Well, I see a dx prime there, so if du is negative dx prime, then dx prime is negative du. So I'm going to replace that in there as well. Similarly, I need to replace my bounds, in other words, going from x prime equals negative L to x equals 0 in terms of u. So that would become a u equals, well, plug in what x prime is there. Well, that would be an x minus L for the bottom bound, and a u equals, well, just x for the top bound. So that's what we end up doing if we actually plug that in. So this becomes like this. So x minus negative L, which is just x plus L for that bottom bound, and then x for the top bound. Now, this is a du over u squared. That is a classic function and if you haven't memorized what the derivative and antiderivative of this function are, you should make sure to do that now. So we know that if we differentiate any polynomial, then we just take the power of the polynomial expression, or the polynomial term, multiply it by the coefficient, and drop the power by 1. Which means if we want to go in reverse, we first we raise the power by 1 and then divide by the new power. So in this case, we have u to the minus 2. So we raise that to u to the minus 1, and then divide by minus 1, the new power. So that ends up giving us a minus 1 times u to the negative 1, or minus 1 over u. And we already had a negative out there from when we did our variable substitution. So the negatives end up canceling, and we're left with this. The negatives cancel, and now we plug the stuff in. If you just looked this up in an integral table, then you would end up still having to plug in what your original integration bounds were, except you would end up getting you would have a different result for the evaluation of the integral because they told you what it was without the substitution. But in any case, we plug in our bounds, so we do a kq over L times 1 over x minus 1 over x plus L. So there we go. We plug in the top bound first, subtract the result from plugging in the bottom bound, and you work it out. On the AP exam, don't you dare simplify this. Just leave it as kq over L times 1 over x minus 1 over x plus L. Similarly, if you're taking an exam in a class or something like that, just leave it like that. But I decided to make this look a little prettier, and I did the whole common denominator thing, noticing that I would get an x plus L minus x in my numerator and canceling out my x's, so it actually does look slightly prettier. And there is our final result here. So hopefully everybody is happy with that. So first, does this make sense? Well, as you get farther away, the x in the x plus L term becomes more and more important. In other words, that's x plus L is going to kind of look more like x. But what if x is close to 0? Well, in that case, you're getting really close to where you have charges. So in that case, the electric field becomes bigger and bigger if you approach the origin arbitrarily closely from the positive direction. So you might kind of wonder about that. It's like, well, in this case, you don't actually have a finite amount of charge at a vanishingly small distance away. So it turns out that the reason that it still blows up is due to the fact that the electric field is proportional to the actual amount of charge, Q, and inversely proportional to 1 over distance squared. So the fact that you have that distance squared down there, even though you're kind of getting close to more and more charge and it seems more and more spread out, well, the spread outness of it is kind of proportional to your distance from it, whereas, because we're talking about a linear charge density, but the actual contribution to each electric field is 1 over distance squared. So overall, you kind of think about a 1 over distance type of thing, and it still ends up blowing up. Okay, and the same would occur also if you approached from x equals negative L from the left. Now, as I mentioned, for beginning calculus students, there are a few people who take this course while they are also taking their first year of calculus. So just keep in mind that you will be provided an integral table on the test. The point is understanding how to turn the physics problem into an integral, and then using some algebra to manipulate your integral into something that's actually in the integral table. So in truth, at the end of the day, all you're really doing here is algebra and then using calculus principles. In other words, the idea that you have a continuous amount of stuff, you need to divide that continuous amount of stuff into infinitely many little pieces, and then you find an expression for one of those little pieces, figure out how it generalizes, and then slap an integral sign in front of it, and look it up in an integral table. Okay, so now let's look at an example of actually using one of these integral tables. Let's say I needed to evaluate this integral. Ooh, this looks kind of nasty. Square root of 12x to the 4th plus 7x cubed, going from x equals 2 to 6. So if you click on this link, which if I am not absent-minded, I'll try to remember to post in the video notes, you'll go to the single page integral table, which I give all of my students. And it looks kind of like integral number 28 in that table, which is integral of square root of x cubed times a linear equation, a first degree linear equation. Well, that's what you would get if you factored out an x cubed right here. You could factor out an x cubed, and that would be square root of x cubed times 12x plus 7. Well, that can be evaluated as long as you have your expressions for a and b. I said times 12x plus 7. Well, apparently a is 12 and b is 7. So all I need to do to evaluate this integral is plug in 12 for a and 7 for b in this particular expression. So there we go. I'm going to plug in 12 for a and 7 for b. And remember, we're evaluating this from x equals 2 to x equals 6, because those were our original integration bounds. So now that we have dealt with this stuff and simplified a few things, we can plug in. The idea is you plug in the top number first, the 6, you get a result, and then you plug in the bottom number, the 2, get another result, and you subtract the 2 results. So here's how we do that. Plugging in the 6 gives you this. Plugging in the 2 gives you the next stuff. And then you evaluate it. And you get this nice looking expression. Now, here's the thing. If you did this, you might not have gotten something that looked like this. But if you were to plug it into your calculator and multiply by 1.0 to make sure you get a decimal, you would get the same result that I got. Don't waste too much time trying to simplify things, rationalizing denominators or rationalizing natural logarithms or anything like that. As soon as you get it to something that can be evaluated, leave it. In fact, even in my case, I just used my TI-89 calculator, which rationalizes this kind of stuff for me. Okay. So that's how you can use an integral table, if you haven't used an integral table before. So now we're going to move on to a situation where the linear charge density is not constant. It's not uniform. So in that case, in the previous case, we had a constant linear charge density. Lambda was equal to Q over L. In this case, I'm going to say that we have a bar of charge, same bar of charge, total charge Q, and the bar has a length of L. But here I'm going to say that the charge density is proportional to the square of the distance from the origin. So in other words, lambda is proportional to x prime squared. Well, that's a proportionality symbol. Well, what does that mean? That means that lambda, the linear charge density, is equal to x prime squared times some constant, which I'm just going to call a. I can call it anything I want, so I'm going to call it a. But I need to figure out what a is in terms of the length of my bar and the amount of charge on it, q. So to figure that out, what we need to do, we need to employ a process called normalization, where we use the fact that the total charge on the bar is q and it has a length of L. So let's see what that is going to look like. In other words, in the first step, we need to figure out what a is, what our proportionality constant is. Well, the total amount of charge there is q. In other words, if I was to add up all of my little bitty dq's all across this bar, they need to add up to big Q. So what does that mean? It means that if I slap an integral sign in front of my dq and integrate from x prime equals negative L to 0, then I need to get Q. Well, what is dq? Well, dq is always lambda dx if we're dealing with a linear charge density. I know what lambda is. That was defined in the problem. That's my proportionality constant a times x prime squared. And notice it's, again, we're doing a primed axis, so dx prime. Okay, well, what does that mean? So I can integrate that. Remember that the derivative of a polynomial is just equal to, like if I needed to take a derivative of a times x squared, that would be 2 times a times x to the first power, multiplying the power by the coefficient and dropping the power by 1. So going in reverse, I raise the power by 1 first and divide by the new coefficient. So raise the 2 to a 3, or sorry, divide by the new power, and then divide the coefficient by the new power, which is 3. So I have a over 3 times x prime cubed. And I'm evaluating that from x prime equals negative L to 0. Well, what does that mean? Well, plugging in the 0, I just get 0, whoopee. So minus, what happens when I plug in the negative L? Well, negative L cubed is negative L cubed, and we have an a over 3 there, so 0 minus a negative al cubed over 3 is just going to be al cubed over 3. And again, the whole time this was equal to our total charge q. Good. I can isolate for a now. My proportionality constant in this particular situation is 3q over L cubed as a result of our normalization process. Okay, so now I know what a is. I'm just going to keep that in mind. So lambda apparently is 3q over L cubed times x squared. And now we do exactly the same thing that we did before. We have dE is k dq over r squared. dq is lambda dx prime. And now I can plug in for my lambda. So there's what my dE is. So I do the same thing as I did before. I slap an integral sign in front of it. And if this is the test or the AP exam, I just factor out that 3kq over L cubed and I look it up in the integral table. Note here that x prime is our variable, so just keep that in mind. X is a constant. It's like 3 or 2 meters or wherever the field point happens to be. Okay, so there we go. That is the integral we need to evaluate. There are multiple ways of solving this. The easiest turns out to be another u substitution. So we let u equal x minus x prime. Well, that means that dx prime is again negative du, just like in the last problem, and x prime therefore is u minus x. The whole point, though, to keep in mind right here is, yeah, we needed to plug in our x prime in terms of our new variable, both for its differential part, the dx prime, and the x prime. So x prime needs to be plugged in as u minus x. And this integral can be evaluated. And also notice that we plugged in we substituted our bounds into our u, so that now we just evaluate it in terms of u instead of having to substitute back later. So here we go. This is a polynomial over a variable, but things can be simplified here. U squared over u squared is called 1. A 2x over u, or sorry, a 2ux over u squared is just 2x over u, as long as u is not 0. And x squared over u squared, we just leave that. And this can be evaluated. This is a polynomial. Now, you might recall that the antiderivative of 1 over x is natural log x. In other words, the derivative of natural log x is 1 over x. So, and it's natural log absolute value x, so if it's u, we have natural log absolute value of u. But yeah, 1 is just 1 times u to the 0. So we raise u to the 0 by 1 power, so u to the first, and divide by the new power, 1 over 1. So we have 1 over 1 times u to the first. There's our u. And there's our 2x times natural log u, absolute value u that is, because natural log is undefined for, or indeterminate for negative values. And again, we have x squared times u to the negative 2. So its antiderivative would be x squared times u to the minus 1 over negative 1. So there's where we got a negative in there. And now we're ready to plug in our integration bounds. Again, remember that x is a constant here. It's that particular point right there. And after doing that and simplifying, we get an expression for our electric field. Yay! We did it! So that is how you would solve for the electric field in the case of a variable continuous charge distribution. The next step to take after this, in terms of increasing the level of difficulty, would be to try to figure out the electric field at some random point in the xy plane due to a bar of charge. But that is going to be a vector type of problem, and that we will save for our next video. So until then, comments and questions in the YouTube comments. Thank you.